To understand dipole-dipole forces, we need to remember how to draw a Lewis structure. We need to know which elements have more electronegativity from the periodic table. And we need to be able to draw a bond dipole or identify which parts of the molecule have delta plus and delta minus in them. Now, dipole-dipole forces are not the strongest intermolecular force like hydrogen bonds, but they're a moderately strong intermolecular force. They're the second strongest force. Now, let's look at this little train here before we understand molecules. You may have experienced personally playing with these toy train sets or seen maybe a little brother or sister or cousin doing the same thing. And, the trains come together one way, but if you try to put it the other way, they kind of don't stick, right? So you have to try it the other way. And kids aren't ever taught this, but they just intuitively just pick it up and learn that, okay, if it doesn't go one way, try it the other way. Now, the reason why is because magnets have a north and south pole, and magnets align one north to the other south, okay? So the north of one magnet aligns to the south of the other magnet, and one way to think of that is just opposites attract. If you try to stick two magnets together with the north and north going towards each other, they repel one another, okay? Similar to this idea that likes repel, okay? Now let's look at molecules here, all right? Polar bonds have a delta plus and a delta minus. Again, remember, a polar bond is a covalent bond built up from two different elements in the periodic table. The stronger or more electronegative element is going to harbor a delta minus, and the weaker or less electronegative element is going to harbor a delta plus, okay? So a polar molecule is going to have an unequal charge distribution. There's going to be one part of the molecule with a delta plus and another part of the molecule with a delta minus, okay? And here's a very simple molecule, hydrogen chloride. We have the hydrogen, which is less electronegative, labeled as delta plus, and the chlorine is more electronegative, and that's labeled as delta minus. And we're putting two of these molecules close together so that the delta minus of one part of the molecule is being attracted to the delta plus of the other side of the molecule, okay? So you could think of that as two, train cars stuck together by magnets, if you want to think about that, okay? And they align the positive and negative to one another, all right? Just to put it another way and to reemphasize this, opposites attract due to electrostatic attractions, okay? And the positive charge and negative charge on different molecules are attracted to one another. And that's a cohesive force that attracts those two different molecules to one another. We want to remind ourselves that Lewis structures are going to be drawn, and then we need to determine if the molecule as a whole is polar. If the whole molecule is polar, we say that it has a net molecular dipole, and it's going to exhibit dipole-dipole forces. This list here is a list of all the things we need to memorize, okay? In my chemistry 111 and 112 course, we need to memorize up to 4 coordinate geometries, okay? So the shorthand notation is AB2. That's going to be linear, and we're going to call that nonpolar. If we have something that's AB3, that's trigonoplanar, and that's also nonpolar. If we have something like AB3U, that's trigonal pyramid, and that's going to be polar. AB2U and AB2U2 are both bent, and they're going to both be polar. And AB4 is tetrahedral, that's going to be nonpolar. Now, for these nonpolar molecules that I've highlighted and underlined, they're only going to be nonpolar if all the peripheral atoms are exactly the same. Okay, so keep that in mind when you're determining polarity. Now let's start doing these problems here. All of the following exhibit dipole-dipole forces except, all right? So CH3Cl has a carbon atom. Whenever you're dealing with carbon, think and remind yourself, where is carbon found on Earth? It's found in the middle of the Earth, or in the Earth, right? And so also carbon is found in the middle of covalent or molecular compounds or organic compounds. So carbon's in the middle. Build up your 3 hydrogens. and place your chlorine. Now hydrogen's in group 1 of the periodic table, so we add 1 valence electron. Carbon is in group 4. Chlorine is in group 7, so we add 7 valence electrons to chlorine. Then what I do is I create bonds by doing this dot-to-dot method I teach in my courses until we achieve an octet. So this is the molecule, and we want to examine now any kind of polar bonds. So we ignore carbon and hydrogen. Carbon and hydrogen have very similar electronegativities, so by all counts, they're pretty much a nonpolar bond, okay, for this analysis. We look at something that really stands out. Chlorine is very electronegative, and so this guy here is going to have a polar bond. That carbon-chlorine bond is a polar bond. We ignore these other ones, and the net molecule is going to have a polarity pointing down on the page as I have it drawn, okay? If a molecule has a net molecular dipole, we say the molecule is polar. If it's polar, it's going to exhibit dipole-dipole interactions. All right? All right, so that guy there has dipole-dipole interactions. How about the next molecule? CH2Cl2. We have a carbon, we have 2 hydrogens, and 2 chlorines. Again, we add the requisite valence electrons onto each of these atoms from the group number that they are found in the periodic table. And then we create a covalent bond by using 2 of the valence electrons. And the other ones we just leave there, right? Now let's look to see if this molecule has polar bonds. A carbon-chlorine bond is polar, okay? That's a polar bond. This carbon-chlorine bond is polar, okay? And these bond dipoles are indicated as vectors, and they add up together to give you a net dipole, you know, kind of pointing to the bottom right of the screen, okay? If a molecule has a net molecular dipole, we say that it's polar, okay? And it exhibits dipole-dipole interactions, all right? Let's look at the next molecule, CH-Cl3. Okay, so again, carbon's in the middle, and we have only 1 hydrogen, but we have 3 chlorines, okay? Put in those starting valence electrons. Create your bonds. Okay. And then we want to examine if this molecule is polar. So chlorine is an electronegative element. So the carbon-chlorine bond is polar. This bond is polar. This bond is polar. And then we switch to a different colored pen to figure out how do all of these vectors add up, okay? They all seem to point to the right in this molecule as I have it drawn flat. But this simple analysis will help us realize that this molecule has a net molecular dipole. It is therefore polar, and it exhibits dipole-dipole forces. So each of these 3 molecules so far are all tetrahedral, but because the peripheral atoms are not all identical, they are polar. Our next molecule is carbon tetrachloride. A carbon atom is surrounded by 4 chlorine atoms. Okay, and let's add in these 7 valence electrons to each of the chlorines. And then let's create bonds to create a nice octet on all of the atoms. Okay, and now we don't need to draw all our arrows. This is actually a tetrahedral molecule, but each of these 4 chlorine atoms is pointing into the corners of a tetrahedron, and therefore these individual bond dipoles all cancel, and there is no net molecular dipole moment. No net dipole, okay? So it's tetrahedral. All of those 4 chlorine atoms are the same. So this is nonpolar. And therefore, we would say this molecular structure or molecule will not exhibit dipole-dipole forces. Okay. Let's do the next problem in this series. Which of these is expected to have a dipole-dipole intermolecular force? So TeCl2 you might be less familiar with. Tellurium is found below sulfur in the periodic table. It's in group 6. Okay. Chlorine is more electronegative because it's found further up in the periodic table. And remember that more electronegative elements are positioned on the outside of a Lewis structure, okay? So the central atom will be tellurium with 6 valence electrons. Chlorine still has 7 valence electrons. We create covalent bonds here by using up 2 of the valence electrons, and we have our final molecule. Now this structure here has a template of AB2U2. What does that mean? The central atom is tellurium. Okay, A stands for the central atom, and B are the 2 bonded groups. Okay, so we have chlorine that's bonded and chlorine that's bonded. All right, and what we have are 2 pairs of electrons left over on the central atom. So the U stands for unshared electron pairs. Okay, so I'll just put 2 dots. And remember, that's for the central atom only. It's not for the lone pairs on the chlorine atom. If I sketch this molecule out in 3-dimensional space, we know that it's bent. All right. Tellurium has 2 lone pairs of electrons. We sometimes call that the rabbit ears because they kind of look like the ears of a rabbit. And we have 2 chlorine atoms, a total of 4 groups on that tellurium atom that are pointed into the corners of a tetrahedron. And this molecule is called bent. We would say that it's polar, and therefore it does exhibit dipole-dipole forces. Okay? So that's kind of how you think about the template, think about the molecular geometry, and then assign polarity to your molecule. It does not matter that these 2 chlorines are exactly the same. Because they are bent, they pull in the same direction. So this chlorine is more electronegative than tellurium. This chlorine is more electronegative than tellurium. So if we draw the net molecular dipole, these 2 chlorines seem to be pulling it towards the bottom of this page. So that's why we say that this molecule has a net molecular dipole moment, and the molecule is therefore polar and therefore exhibits dipole-dipole forces. CO2 is the next molecule. This might be very familiar to you. Carbon again is in the middle. Oxygen is more electronegative and positioned on the outside. Oxygen has 6 valence electrons because it's found in group 6. Carbon is in group 4, so it has 4 valence electrons. In order to construct a Lewis structure that satisfies the octet rule for all the atoms in this structure, we need to create 2 double bonds, one on the left and one on the right. And in this structure, there are no lone pairs left over on the carbon atom, so it is perfectly linear. Let's look at the individual bond dipoles. This carbon-oxygen bond is polar. This carbon-oxygen bond is polar. But if you add up those 2 as vectors, you can see that the net molecular dipole moment is 0. They cancel each other out. Okay? So we say that this molecule has no net molecular dipole moment. Okay? And therefore, it's nonpolar. And therefore, it's not going to exhibit dipole-dipole forces. This would be like a toy train without magnets on it. It just wouldn't stick to another toy train without magnets. Our next molecule is BCl3. Okay, boron trichloride. Boron is a less electronegative atom than chlorine, so we want to position the 3 chlorines around the boron. Chlorine, as we've already seen numerous times today, has 7 valence electrons. Boron has 3 valence electrons, and it's not going to satisfy an octet. It's a violation of the octet here. But when we create the covalent bonds to the boron atom here in the middle, we stop. And if we look at this template here, we would label it as AB3. Each of these 3 boron-chlorine bonds are polar, but they cancel in a way that there's no net dipole. Okay? The whole molecule as a whole is too symmetrical because all of these 3 chlorines are exactly the same. It's trigonoplanar, it's nonpolar. Okay? So again, nonpolar molecules do not have dipole-dipole forces. Ch4, we've seen this before, and we'll just sketch this out quickly. Here you can see that the atom is symmetrical. All of the peripheral atoms are the same, and it's tetrahedral with no lone pairs left over on the central atom, so this is a nonpolar molecule. Okay, nonpolar molecules have no net dipole. They do not exhibit dipole-dipole forces. So I hope these 2 problems have helped you. This is a tremendous Cliff Notes presentation of dipole-dipole forces, but I hope it gets you started.